This video will introduce the Fourier transform, its mathematics, and talk a little bit about how we think about it. So you'll notice I've already put on the screen the definitions associated with the Fourier transform. So this first line is the Fourier transform. It takes a signal x of t, which is a time domain signal, and converts it into x of omega, which is the Fourier transform of this time domain signal. For those of you that are interested in this sort of thing, the Fourier transform typically has a capital letter to represent it, and you'll notice that the x over here is taller than the x over here. To take the inverse Fourier transform, I can use this formula. And you'll notice that the integral for this formula looks much the same as the integral for the forward transform, that is, going from the time domain to the frequency domain. Going from the frequency domain back to the time domain is actually pretty similar. I don't have the negative sign on the exponent, and I integrate with respect to omega. But again, given a transform x of omega, this will give me x of t. And I represent the fact that x of t and x of omega are related through the Fourier transform by this notation. Now, in terms of understanding how the Fourier transform works, the first thing to pay attention to is the fact that x of omega is generally a complex valued function of omega. So for every value of omega, this x will have a real part and it will have an imaginary part, which sometimes can be somewhat confusing. It also makes it quite difficult to graph x most of the time. So what we typically will do is we will define what's called the magnitude spectrum, like this. And this is basically the magnitude of the complex value that x has. So again, the magnitude means that if I have a point in the complex plane, let's say this point right here, then the distance from the point to the origin is the magnitude. Okay. We will also define, I seem to sort of run out of room, let's see if we can just tuck it in here, what we call the phase spectrum. And this is the angle that the complex number makes with the real axis. So in this particular case, if I have a complex number that's out here, the angle that it makes with the real axis would be the phase. Typically you express these phases in radians, and they'll typically have values that go from minus pi to pi. Okay, and again, because quite often we're mostly interested in the magnitude of the Fourier transform and how it behaves at different frequencies, we will plot just the magnitude spectrum. We'll plot just this guy, and then we'll talk about this as if it were the whole Fourier transform. Now, sometimes that's useful, but it's also technically wrong. In order to know what the whole transform is, I need to know both the magnitude and the phase of the Fourier transform. Or equivalently, if I know the real and imaginary parts of the Fourier transform, that gives me the same information. So, the next thing to discuss is that the Fourier transform, as we've just described it, is very closely related to the Laplace transform. So the Laplace transform has a definition that looks like this. X of s is the integral from minus infinity to infinity of x of t e to the minus st dt. This is the bilateral Laplace transform. And you'll notice that if I replace the s right here and here, actually we're replacing it here, by j omega, then I essentially have the same expression that I had before on the previous screen. X of omega is this integral from minus infinity to infinity, x of t e to the minus j omega t dt. So if I already know the Laplace transform of a particular time function, then I can find its Fourier transform very easily. So as an example, suppose that x of t is e to the minus at u of t. So this is a decaying exponential that starts at 0 and then decays with a rate given by a. Those of you that have already studied Laplace transforms will know that the Laplace transform of this is just, well, let's actually write it out. X of s is 1 over s plus a. Okay, so this is the Laplace transform of this time function. Using this result that we've just looked at, we can say that x of omega is equal to 1 over j omega plus a. So there you have it. Possibly your first Laplace transform, and that was pretty easy, wasn't it? So what I'd like to do now is plot the magnitude and phase spectra of this x of omega. So I'm going to try to do this online in the video using MATLAB. If it gets messy, you may discover that, or I may pause things and do some stuff without putting it on the video. But so we bring up a MATLAB window. The first thing we're going to do is define omega to be a vector of values from, say, about minus 5, I'm just making that number up, to 5. We'll define a to be equal to 2. Seems like a nice value for a. And then we'll define x of omega to be 1 over j times omega plus a. So if I've done this correctly, we should now be able to plot the magnitude, and in MATLAB this is ABS, of x. And there you have it. Okay, this is a plot of the magnitude of x of omega. And in fact, yeah, so basically, well, this is actually not a very good plot. Let's fix it so that it shows us the omega values as well as the x values there. That should be better. And let's see if we can get that to come up to the front. There, now we have it. So you can see at a value of omega equals 0, it has its largest value, which is 1/2, and as omega gets large, either positively or negatively, it goes to 0. I can also plot or do the phase plot. And there you have that. You can see that at 0, the phase plot is 0, and for values of omega that are negative, I get a positive angle. For values of omega that are positive, I get a negative angle. So there you have it. That's a plot of the magnitude and phase spectrum of this Fourier transform. One last comment, and then we'll be done with the video. This x of t that we've used here is if you've done Laplace transforms, you'll remember that this is the form of the impulse response of an RC circuit. And it turns out that we use these quite often as fairly crummy low-pass filters. If you recall, the magnitude spectrum was largest when omega is equal to 0, and then it tapers off as omega gets large, either positive or negative, which makes this, again, a crummy low-pass filter. So with that, we'll end this video.